Okay, let's look at signed number now. So far, all the examples that we were looking at, they were all only like positive numbers or unsigned numbers. So obviously we need to have like some negative numbers also, and there are different ways that they could be represented in hardware. So these are like the possible scenarios that we could use to basically represent the unsigned number, so a positive or negative number in hardware. And also we need to be able to do some arithmetic with them. So we are like adding, subtracting, multiplication. So we are doing all these arithmetic operations are signed and unsigned numbers. So there are three ways that we're gonna look at. There's the sign magnitudes, one complements and two complements. What is actually being used in MIPS processor is the twos complement, and that's basically going to be our focus. But we're going to look at these first two to see how we got there and how they are different. So let's look at sign magnitudes. So this is very simple. Basically, the idea is that we are reserving one bit, the most significant bit or one digit of this binary number, and that's gonna indicate if our number is positive or negative. So it's very straightforward. If it's 0, it's positive. If it's 1, it's negative. So for example, these two numbers that we have, you see that all the bits are the same, and we're going to calculate that same method of indexing and multiplying. We're going to get 53. But we know that this is a sign magnitude numbers, so this is something that we should know that which system we are working on. Like just looking at the number, you're not going to know that this is going to be a sign magnitude method. But knowing that, you keep this aside, this one, you say, okay, there is a negative number, and then you're gonna continue with conversion, and then you calculate your 53, and then you put the negative back. So 1 is negative and 0 is non-negative or positive. So here is another example. So we have the leftmost significant bit is 0. That means a positive number. And then you calculate all of these as usual. You get your number, and that's going to be positive. So very straightforward. If we are looking at the number 0 itself, we could have actually two representations. We could have this, let's say if you have 4-bit, and also we could have this number, so 1000, and both of them are actually representing 0. So this is like positive 0, there is negative 0 in this representation, which is not ideal because like negative 0 does not mean anything for us, right? Like 0 is, I think, is not negative and not positive, so it shouldn't be really in this way. And also, like on top of that, if we are adding, let's say 5 plus minus 5, which is supposed to be 0, we are not getting that. So 0 1 0 1, and then there is positive 5, and then this is negative 5 because it's the same number, and then only this bit is changed. If you're adding this, how we talked, so 1 plus 1 is 0, carry 1, drop, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1 is overflow, so that one is discarded. Whenever you're working, let's say 4 bits, anything that is extra overflow, it's gonna be discarded. So that is not 0, that's gonna be 2. So there's something off, like we cannot directly work with this. Of course we could like convert this and like do some other operation and get around with that, but if we just add them, it's gonna be we're not gonna get 0. Okay, so here we have one's complement. That's the second method that we're looking at. In one complement, also the leftmost significant bit is showing if the number is positive or negative. So same way, exactly as what we had before. To calculate from a positive binary number to ones complement, you basically flip every bit. And that's going to be the representation of the same number, same positive number as if it was negative. So let's say you have a decimal number and you want to convert this number to binary in one's complement system. So how you do that? We have two cases. So let's say we have, I'm gonna try to write here. So let's say we have number 10. So here we have number 10. And so that's like positive. The first thing that you do, this is in decimal, you get it to binary. What is 10 in binary? We know that's 1 0 1 0. So this is the positive number 10. And if you're converting it to one's complement, this one looks like a negative, right? Because the left most significant is a 1, but we want to actually show number 10. So it has to be, if we are showing it in one complement, we convert that, but like you have to make sure that the last one is not, it's not 1 because it's a positive number. So we have to pad it. So basically this is going to be your number. If it was negative, what you do, you basically calculate the positive value, which is going to be this number, and then you flip every bit. So this is going to be 1 0 1 0 1. So you flip. So basically that's the general rule. And you always have to make sure that you have enough bits to represent that number. So if I tell you that in one's complement you want to show positive 10 with only 4 bits, you cannot do that. It's out of range. So that's not possible, right? The maximum number that you can have with 4 bits, what is that gonna be? Like pause and try to answer that. Maximum number, maximum positive number that you can have with 4 bits in one's complement. It's gonna be 0 because it's a positive, and then you have 4 bits. So you go all of them 1, 1, 1, 1, right? So that's 2 to the 0, 1, 2. So 4 plus 2 plus 1. So that's 7. So that's the maximum value that you can represent in the system with only 4 bits. So 10 is out of range with 4 bits. So that's why we have to pad it with 0. Here we don't have any constraint, so that's okay. 56 in decimal is positive. We want to calculate the ones complement binary. So 56 is positive, so no bit flipping needed. So basically you just convert this one. We had two methods. You either do 56 divide by 2, and then you get some number and the remainder some number and you continue, or you try to find the largest powers of 2 in 56 and you go in that method. So but after you get that, this is going to be your number, and you have to just make sure that the most significant bit is a 0 because your number is positive. But other than that, you don't change anything. What if it was minus 56? So these two first steps is actually the same. And after that, to show that is a negative number, and that's one's complement rule, you basically flip every bit. So it's going to be basically the inverse of this. So 1 1 0 0 0 1 1 1. So it is 2. So now let's look at the other way. You have a one complement number, you have a binary number, and you want to get the decimal value of that. So this is exactly, we do basically the opposite. So let's look at it. We have this number, and is it positive or negative first? So we look at this last zero, that's a sign bit, and that's a 0, so that means that is positive number. And when we want to get it to decimal, we basically do the same indexing stuff. So 0, 1, 2, we have a 3, 4, and 5. So we get 32, 16, 8. Add them up, you get 56. So that's your decimal number. Nothing tricky. But in this one, again, you have the one complement binary. It's a 1 on the most significant one. So what do you do? So basically, we are going like this way. Once you see it's 1, that means it is a negative number. So that means it's already been flipped. So we have to flip back, basically, to get to the original number that it was before getting flipped, because that's the number that you want to convert. So as soon as you see this 1, you flip every bit, and this is what you get. So this was your original, and then this is the flip version. Then you convert this number to the decimal value. And then, because you know it was a negative number and you did the flipping, you just add the negative sign back. So you get minus 56. So basically, that's all the cases that you can work with in ones complement. What is the case now with the 0? So we still have two representations for 0, and that is, well, zeros, and then we have all ones. So both of these gonna be 0. So because if you convert this one, we're gonna flip, and then 0, 0, 0, 0, if you just follow the same rule. And then you calculate the value of this, that's gonna be a 0, and then you add that negative sign, so you get negative 0. So you have two zeros, so that's not so good. And then let's look at the other example that we had. So if you add 5 plus minus 5, we have these two numbers, and these are represented in one's complement. So there is one complement, it's going to be the same, is a positive number. This one is, if you flip these, you see that it's going to be 0, 1, 0, 1, and it's a negative. So that is 5. There is negative 5. If we add them, we're going to get all ones. And it's not surprising because like there is the flip of that. So of course we're going to get all ones. But then when you calculate the value, this is going to be minus 0. Not so bad, but still we can do better. So let's look at the next method. So let's look at the two complements that is basically fixing that issue of there is 0 in one complements. I want to show you a quick example, and let me write the 3 bits number that we have 0, 0, 0. So if we look at this, and let's say this was one's complement, what would be the value? This is 0, this is 1, this is 2, this is 3. So far so good, right? This is 2 plus 1. What about this one? This is gonna be 0, 1, 1. What is 1, 1, 3? And it is a negative, so it's negative 3. Then we have 1, 0, 1. So this is gonna be 0, 1, 0, the flips of it, and that is negative 2. This is gonna be 0, 0, 1, so that's negative 1. And then this is 1, 1, 1, which is gonna be 0, 0, 0, so that's kind of like negative 0. So if you look at this, we have basically 8 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. But the problem is that we are wasting one position that we have here because we have double 0. We have positive 0 and negative 0. And we know that we cannot do better than 8 with 3 digits because that's all the combinations that we can get. But this is a waste. So two complements is trying to save this basically space by shifting everything. So you will see what I mean in the next slides. So how are we gonna do it is that the positive is the same still, and also still is the same. The leftmost significant bit is the sign bit. The positive number is the same. If it was negative, we're gonna take the one complement and add one to it. So let's say we have like -5 and we want to calculate that number. So we first calculate 5 in binary. So 5 in binary. And then we flip that because it's a negative number. So that's going to be one complement. And then we add 1 to it. That's going to be our 2 complement. So this is kind of like a smart way to fix this issue of the 2 zeros. And it works out really good. So example, we have a -50. That's the representation, just the positive. And again, you have to make sure this last one is 0. Otherwise, it's going to mess up your sign. You calculate the ones complements, and then you calculate the twos by just adding 1. It is just +1. Same thing here. So one complement is just the flip. So if I want to write it here, there is flip, and then add 1. So that's 2 complements. And basically that's how it's gonna shift everything by 1 to fix this issue of the double zeros. So this is binary to decimal, so it's the other way around, and we are basically like doing this the opposite way to get back to where we were. So if we have the leftmost bit, the sign bit, if it's a 0, that means it is just a positive number. So we just convert it, nothing new here. If it was 1, we take the 2 complements again, and then we calculate that. So taking the 2 complements of a number and then taking the complements of that, it's gonna be basically back. So for example, if you have, so a here, if you do 2 complements of a, let's say you get a prime. And then if you do again 2 complement of this, you're gonna get a back. So that's gonna work. So that's why. So once we have this 2 complement, so we know it's a negative number if that is 1. So we just take the 2 complements again to get the original number back. And then we calculate that number as if it's a positive number. So our regular powers of 2 and so on. And then you just add a negative sign to it. And that's gonna fix the sign. And here are some examples. Okay, so these are 2 complement binary number. And again, always I will tell you, or you should know which system you are working on. It's not nothing that you can know just by looking at the numbers. You should know like this is the 2 complement system that they're working on. So basically these are 2 complements, and we want to get the decimal value of those. So this is my number. I see it's a 1, so I'm gonna take the 2 complement, which means flip +1. So I'm gonna get this one. This is gonna be 1. I knew it was a negative, so I add a negative sign back. Then I look at this one. It's a negative number, so flip, add 1. I'm gonna get this. So we calculate the value, powers of 2, adding them, we get 93. We know that it was a negative number to begin with, so we add the sign back. So these are all the same examples. Positive numbers, there is nothing to it. It is positive, we haven't done 2 complements on it, we just put it as is. So we just do the powers of 2 and add. And very simple. So this is a good thing that I wanted to tell you. So since we add that 1, we only have 1 0 now. And if we are not adding the positive and negative, so the same example that we had, we're going to get the perfect 0. So we don't have 2 zeros, negative 0, positive 0. So this is like perfect. And another thing, that if it was an overflow, so let's say we had like, so this was a 1, let's say here, and you're adding and there was an overflow, you just discard that. It's gonna work perfectly. So sometimes like it happened that you have that situation and you shouldn't worry about it. So it's gonna take care of itself. One quick thing here of that example of 3 bits that we had. So let me write them again. So we had 0 0 0. Let's do the 1 complement and then 2 complement. So this was 0 1 2 3, and then this was, I did it before, so it was -3 -2 -1 and -0. In the 2 complements, this is gonna be same. So 0 is 0, 1 is 1, this is 2, this is 3. So nothing new here, right? Is it positive? We are doing the same. Let's look at here. So it's 1 0 0. So we said flip, add 1. So it's gonna be 0 1 1 plus 1. So it's gonna be 0 0 1. And we calculate this number. So what is this one? It's 2 to the 0 1 2. So 4. So it's actually -4. So from -3 we got to -4. Let's look at this one. 1 0 1. Flip, add 1. So the flip is gonna be 0 1 0, and then add 1, gonna be 0 1 1. What is 0 1 1? So it's 2 plus 1, so that's 3. So -3. So you see it's added 1. This one gonna be 0 0 1, add 1, gonna be 0 1 0. So that's 2. And it was negative, so -2. And last one, it's gonna be flip all zeros. So 0 0 0 plus 1, 0 0 1. So that's 1, and then add a negative, so -1. So that's how that in the 2 complements we got this extra part. Basically this part shifted. So we have one more number that is -4 now here that we didn't have it in 1's complement. So now we have 8 different numbers, and there are 8 combinations of these that we can produce. So it's perfect. So here we can see the range of the signed and unsigned numbers, and you notice that it's shifted. So for example, we have here 128 minus 122 to 127. So that's still 256 different numbers. But because we have a signed number now, the maximum value is almost like roughly half, comparing to the same size, like both of them are 1 byte, which is 8 bits. And basically the range is shifted, and the maximum value is 255 in the unsigned, but on the signed is 127.